I have here 3 equations of 4 unknowns, and you can already guess, or you already know, that if you have more unknowns than equations, you're probably not constraining it enough. So you're actually going to have an infinite number of solutions, but those infinite number of solutions could still be constrained within, well, let's say we're in 4 dimensions in this case, because we have 4 variables. Maybe we're constrained into a plane in 4 dimensions, or if we're in 3 dimensions, maybe we're constrained to a line. A line is an infinite number of solutions, but it's kind of a more constrained set. So let's solve this set of linear equations. And we've done this by elimination in the past. But what I want to do is I want to introduce the idea of matrices. And the matrices are really just arrays of numbers that are shorthand for this system of equations. So let me create a matrix here. So I could just create a coefficient matrix, where the coefficient matrix would just be, let me write it neatly. The coefficient matrix would just be the coefficients on the left-hand side of these linear equations. So the coefficient there is 1, coefficient there is 1, coefficient there is 2. And you have 2, 2, 4, 2, 2, 4, 1, 2, 0, 1, 2. There's no coefficient on the x3 term here, because there's no x3 term there. So we'll say the coefficient on the x3 term there is 0. And then we have 1, minus 1, 1, minus 1, and 6. Now, if I just did this right there, that would be the coefficient matrix for this system of equations right there. But what I want to do is I want to augment it. I want to augment it with what these equations need to be equal to. So let me augment it. And what I'm going to do is I'm going to draw a little line here and write the 7, the 12, and the 4. And I think you can see that whatever this right here is just another way of writing this. And just by the position, we know that these are the coefficients on the x1 terms. We know that these are the coefficients on the x2 terms. And what this does, it really just saves us from having to write x1 and x2 every time. But we can essentially do the same operations on this that we otherwise would have done on that. So what we can do is we can replace any equation with that equation times some scalar multiple plus another equation. We can divide an equation or multiply an equation by a scalar. We can subtract them from each other. We can swap them. So let's do that in an attempt to solve this equation. So the first thing I want to do, just like I've done in the past, is I want to get this equation to the form of where if I can, I have a 1. My kind of leading coefficient in any of my rows is a 1. And that every other entry in that column is a 0. And in the past, I made sure that every other entry below it is a 0. That's what I was doing in some of the previous videos when we tried to figure out if things were linearly independent or not. But now I'm going to make sure that if there's a 1 and if there's a leading 1 in any of my rows, that everything else in that column is a 0. And that, what I'm calling, that form I'm doing, is called reduced row echelon form. Let me write that. Reduced row echelon form. And if we call this augmented matrix matrix A, then I want to get it into the reduced row echelon form of matrix A. And matrices, the convention is, just like vectors, you make them nice and bold, but use capital letters instead of lowercase letters. And we'll talk more about how matrices relate to vectors in the future. But let's just solve this system of equations. So the first thing I want to do is, in an ideal world,